your Zoom is connected.
And then should I change the camera? Right?
Yeah, it could even be on Zoom when you have stop video.
Oh, yeah.
It's
How do I?
it should be
This is one.
okay.
Yeah, cool.
I can see
So-
as well as
Oh, yeah. I can stay here in the corner.
we can see it move. But just tell me I can move it a bit.
I can stay here in the corner. This is fine, so that I don't get into the live, but I can still switch here. Thanks. All right, so it's so great to be here. Really, thanks David, thanks Katia for inviting me. So finally, after 20 months, roughly, I had the thrill and that little bit of anxiety, to speak in front of an audience, because all that is kind of canceled out. But of course, it's really great that you guys have decided to go for a hybrid mode, so that to give opportunity for people that are remotely attending the conference. I guess this is the best, we can do, exploiting technology at full speed without losing our need for social interaction at a distance, of course. And but more importantly for me, I could actually try to understand if after 20 months I could still fit in my jeans. And like half of the country probably, I started making sourdough bread. I even enrolled in the class. I'm making focaccia pizza. Of course I'm Italian, right? So I had to do that. But it was really reassuring, barely fitting. The jeans I'm holding my breath, but so don't get it too hard.
That's why you stand, right? You
want exactly, because it'll be too much, all right, so I would like to talk to you about something. So this is, the ability to crack some joke. This is what makes a live event so interesting for me. So I wanted to talk to you about. So there are some things in common that I want to make on Luke's presentation. It's a good comment. So it's a kind of a follow-up, something I thought about while he was talking about it. Not to be for the final part. So what I wanted to talk to you about is adversarial machine learning attacks, so the basic test-time attacks, but something a little bit different from the usual Panda images that we see that you had some carefully crafted noise. I do have that picture of them, of course. I do have that picture in the slide, but it's slightly different. So, and what we were interested in is about trying to understand this in the context of what we call problem space transformation. So in the context of realizable attacks, because this is what matters most of the times, it's not important to perform an attack in the feature space. If at the end of the day, you need to have an object that retains maliciousness, that retains the ability to bypass the system. This is a lot more simple to accept in some specific application domains, but in others, it's a little bit trickier to understand. So, and I'll try to tell you also some anecdotes as I go along. So let's see. So let's imagine like a dystopian future. Like if this 20 months was really enough, something even worse, where pandas are just banned from our city, like those cute little pandas, because they're just too cute, right? So they just banned from the city. And of course, the city, we live in a dystopian future, nothing as realistic as we have right now. So there's full of CCTV around that actually tries to see whether there are pandas around. Panda are bad, they're too cute, and they have to be banned, right? And this CCTV systems, of course, rely on computer visions, and underneath, of course, deep learning systems to identify segmentations and identify pandas because they want to be banned. And so this is really, really great. But what we could do is that we don't know, but panda chewing on this bamboo sticks for the entire life and sleeping a lot, they're actually quite smart. So they're quite fond in maths, and they do remember that there was one interesting seminal paper that explored some intriguing properties of neural networks. And therefore, so Panda, armed with this knowledge, they remember saying, oh, interesting. So I can actually try to camouflage myself, right? So I can add some makeup noise and try to fool these systems. Of course, this noise is not random noise, it's just optimally found noise defined to solve an optimization problem. In general, there are slightly different ways, but in general, this is kind of the gist. And the panel said, cool, I can do that. And of course, I don't live in an image world, I live in a real world. So I don't need this random noise, I do need a mask, right? So the optimal solution is this random noise, but it's all right, I can actually go to a costume shop and try to settle for something that is as good enough, right? So because the optimal noise doesn't exist. in the real world, it might not exist. You might need like a printer that print out that specific pattern with that specific resolution to actually fool the system optimally. So you have to settle for something that is still good enough, right? And therefore, the panel said, this fox mask is okay. So I'm going to wear a fox mask, and all happy and chubby, but pandas are chubby, and it goes around, and unfortunately, something bad happens though, because there's a lot of artifacts that even with the fact that there's still a panda underneath. Okay, so there's the panda paws, the big chubby belly, the panda typical pattern on white and black. So these all are artifacts that give away that semantically we're still talking about a panda. So in the real world, things are a little bit more complicated because the transformation you have in this ideal representation that we do have consequences in the real world. And I guess we need to start thinking and reasoning about that in a little bit more principled way, because I know that depending on the work on the field that you work in, this is kind of it goes without saying because it's natural to understand that. But in other fields, I guess it was a little bit of a best effort. So what we started observing, especially in the security community, is that you see a lot of adversarial attacks on images, of course, some in audio domain, and that's people started looking at software, of course. And then people say, I add some random bytes at the end, some tweak here, tweak there. Is it enough? Is it what we need? Or do we need more? Academically speaking, to understand the problem better, but also from a practitioner perspective. And this is where we started with this journey. It lasted, it's still ongoing because it's part of the research vision of the lab, but we started out with something very more pragmatic. Let's say, okay, let's try to take a piece of software and then transform it in such a way that the transformation corresponds to perturbations, and we can bypass systems. And that actually worked as a feedback loop because we realized that the problem was a little bit more complicated than we had imagined. And we wanted to sort of come up with a principled way, perhaps a reformulation of adversarial machine learning attacks in the context of problem space attacks. And so let's see what happened, like very quickly. And of course, you have the original panda image that is represented by X, which is a feature vector, and then you find out this optimal perturbation delta, you have them together, you have adversarial image. Usually the idea to find delta is to minimize our optimization problem. For instance, you don't want to you want to keep the number of perturbations to a minimum, and you want to make sure that the loss of the target class is minimized, like if you want to be clearly specified as that class. Okay, so this is interesting because we always reason, when we talk about adversarial machine learning attacks, we always reason in the context of a norm perturbation, right? But is it true that we need always to consider a norm perturbation? What are the consequences, not just in the attack, but in the defenses? Because everything we have so far, the most promising solutions, if you think about verifiable AI, the reason about epsilon sphere of guarantees, it's always bounded one way or another. So I guess this was interesting and intriguing for us. And say, okay, let's see what happens in the context that is slightly different. So images is a peculiar, images and audio, they're quite peculiar because the input space is provided as a representation learning, the network learns relationships, and everything works very well because it's all continuous or the derivable differentiable, so it can be inverted, so the attack works smoothly. Now in software it's not exactly like that. We've had situation, of course, where people started feeding binaries to neural networks. Still don't know what are really the consequences. Explainability could be useful. This is the thing I want to mention about explainability, because there's been attacks on explainability as well, adversarial attacks on explainability as well, so that using 2020 has a nice paper on that, so that you can't necessarily trust explainability, unfortunately. But so we just wanted to understand what happens here. And in the problem space domain, take software as an example. You have an application. Usually, you need to define some feature upfront, some feature engineering. Again, with neural network, I know that people start fitting this as a whole. There's a lot of consequences there because you don't really know what the network really learns, whether it learns artifacts. whether it's robust against drift, whether it's robust against other types of challenges. So it's a little bit tricky. But in general, you do need to perform this abstraction. Then you have your feature vector X. In the same way you would perform the attack normally as you would do in the traditional adversarial machine learning attack. But here, perhaps it's no longer necessary to make sure that the perturbation you introduce is minimal. You're not changing the visual aspect of an image. You're not changing the semantic of an audio medium, which you don't understand, you clearly understand that it's corrupted. Here you're changing software. What does it mean to corrupt software? What does it mean to add things to software? Can you see it? But perhaps there are other important constraints you need to consider, because you need to make sure that your transformation that induces perturbations in the feature space is plausible. So a piece of software has to resemble a legitimate piece of software. It has to maintain functionality. Does it crash? Because if your transformation make it crash, yes, you're successful to perform the attack, but it's no longer a threat. So the threat model has to be realistic. Does it preserve the malicious functionality? This is another important point, because if your transformation requires to remove, for instance, features, you might accidentally actually cripple the malicious functionality that's provided. So it's no longer making sure that perturbations are minimal, because we want to corrupt how people perceive an image. It's about making sure that everything that you do still is legit. And what we're going to try to understand is what are these constraints and what is the effect of these constraints in the attack, and therefore, of course, in the context of the defenses. So there's another interesting problem here, that whereas when you have an input space, an input image, for instance, and you want to perform an adversarial attack, it's fairly simple because you basically traverse the gradient, you backpropagate the gradient information back to the input. And here, what does it mean to do that? Like, you have this initial abstraction from the software to these features. How do you go back? How do you invert that? Usually, this is non-invertible, this transformation. The feature mapping is usually non-invertible in these cases. So what do? Is that a generic process? By the way, I'm throwing many questions. I will give you very little answers, okay? So don't set your expectation too high. If you want to read this about, of course, the paper, it's something we published last year. It's a fairly dense paper, and it took us a year and a half-ish to work on it, and we're still working on reasoning it. So, let's start to talk about the elephant in the room, survey. So when you do have an image, as we mentioned, the process of going back is fairly simple because the feature mapping is differentiable. In the context of problem space, which for this example is code, but it could be any other realistic example that you have, like sensors that read data. I mean, that information still has to make sense. Like, you can manipulate, those are numbers, you can do whatever you want, but at the end of the day, they have to make sense. So here, this is a little bit more complicated because the feature mapping is neither invertible nor differentiable. So it's a bit tricky how you do that. So back then, we found many people that started to work in this field, trying to give an answer. So we find a solution for work that explores this on Android malware, Windows malware, PDF malware, network traffic even, which is fairly interesting, right? What we found is that it was really hard to compare the state of the art. It was really hard to understand which was the state of the art and how to compare them, because again, everyone was concerned about this minimal perturbation, neglecting the implications in the context of realizable attacks. So we said, okay, and bear in mind, we started off the same way. So we started off, these are Android applications, we had a very large data set available. Let's try to do manipulation and see what happens. And then we had to, this started as an MSc project. So we had to go back a little bit, and we understood that maybe we need to reformulate this properly. And this is basically what we tried to do. So we propose a reformulation of adversarial machine learning attacks in the context of problem space, which anyway encompasses adversarial evasive attacks as we know about. Simply put enough, for specific attacks in each domain, some constraints are already guaranteed to be true. So that you don't have to do much about it. But considering that, it's just a complete formalization. We also find some relationship between feature space and problem space attacks, which I'm not going to be bothering about. So there are a couple of theorems in the paper. Basically says, if you have a feature space attack, good, you can go ahead. If you find an approximation for the inverse feature mapping, then you can find a problem space attack. If you can't find a feature space attack, don't bother, because you won't be able to do anything. You have different search strategies. You can do this starting from the feature space to the problem space, or starting from the problem space, which is a bit trickier, going back to the feature space. But at the end of the day, you need to have an attack in the feature space, because this is what the machine learning eats. And then we tried to identify some actionable points. And on top of this, we decided to try to go for an end-to-end system. Okay, now that we have that, can we actually create an end-to-end system to create adversarial attacks in the context of Android malware in this case, that bypasses classifier, not only vanilla classifier, but also hardened classifier. So classifier that were hardened to withstand some form of adversarial. And we'll see that the problem is because all of this make a reason about bounds. And here you're pretty much unbounded, but you need to consider the implication of this, because you can't just add features. These features will introduce some interesting side effect that we'll see in a second. For the sake of the talk, everything I'm just going to mention is about evasive attacks. So no poisoning, no backdoor, no intermodal inference, not this whole lot of new interesting problem there. And the example is on code. Okay. So in terms of formalization, so let's see the problem space constraint that we believe we need to consider when reasoning about this. So first, you need to identify the available transformation. So how can you alter the problem space object in a fruitful way? And for instance, you can, again, the topic is software. You can, for instance, add APIs, add strings, add bytes. You can remove them, of course, or you can combine addition and removal to change some of these values. This doesn't tell us anything about semantics. Okay, this tells us just about transformation. So we need to manipulate the software, because this manipulation will induce perturbations in the feature space. Good. This is not enough, because the software might crash, functionalities might not be maintained, semantics might be broken, etc., etc. So another set of constraints that we need to have a look at is preserved semantics. So if you look at this very simple control flow graph, it's just a surrogate control flow graph. You have the blue nodes that will lead you to the malicious one. Okay. First, knowing which one is benign and malicious is already a problem on its own, but let's imagine that you know this, right? And the edge is just a straight line that lead you exactly to the malicious functionality. So you could remove edges if in the process of your attack, you find out that actually that transformation corresponds to a valid perturbation that would bypass the classifier. But removing edges here, any edge will actually cripple out the malicious functionality, because the red node will never be reachable. So in this case, it's safer to add edges, as many as you want, to add nodes, as many as you want. We're not talking about plausibility yet. We're talking about semantics here. In this case, semantics are preserved, because you can always reach the malicious functionality. Now, everything that you add doesn't have to interfere with the normal behavior of the program. It's another challenge, okay? That's why we need to make sure that this is plausible. This is the next constraint, but there's one little statement I wanted to make in this point of preserved semantics. This is hard. We know that semantics equivalent is undecidable in the general, but we know, because of computer science, that we need to live with approximations. And we can do all our best, so we can try, if we have a test suite or if we have a way to stimulate the application properly, we can try that. And if we know that the malicious software has to contact the command and control server, has to delete that register key, has to spawn that process, okay, cool. If we see this event, then it passes our ideal definition of semantics, and it's okay. Or we can try to do this by construction, and we'll see what I mean by construction. But to give you, like, a forward reference to the next step, what we've done basically in the Android malware, we added code, we guarded this code with an opaque predicate that is never executed at runtime, and it's hard to identify statically the outcome of this object predicate. But the system that we were targeting performs static analysis, a very lightweight static analysis to extract the features. So our modification influences the feature space perturbation, but it's not executed at runtime. It's an assumption. I understand you say you're kind of cheating. Yeah, the problem is fairly complex, and I understand. We want to get there slowly. And also, I mean, by no means we have finished everything. So there's a lot of work to do there. Okay, so plausibility is what I meant earlier. Like, cool, you can add all of these things, but are you actually giving away the fact that something dodgy is going on? For instance, you might have too much code that is unreachable. For instance, the size of your app might be completely off the chart compared to the average size of an application. And again, we're talking about code, but you can name it and you can think about your domain specific need. And here's the same thing. Like, it's very hard to guarantee this. You either define test suite or you can define it by design, depending on the context. And some things that usually is neglected, that we find that it's useful to explicitly include as a constraint. We have to be also robust to pre-process. Like, if you have heard about a silence attack, that was a deep learning systems that was bypassed very easily because the adversaries added bytes at the end of the binary. Okay, there's no reason why you should be having bytes at the end of the binary. So you can already have a very simple pre-processed analysis that actually strip off all these inconsistencies. Okay, because you don't have to have raw bytes at the end of the binary. So if you strip them off, you already take away the attack, so the attack doesn't even get to the ML pipeline. So you have to be careful about just a little bit. Okay, now this is interesting, and I guess this is kind of the core of everything. All this transformation induce something in the problem space, and therefore that has reflection in the feature space. Now let's just simplify and let's use about two features. Okay, it's easy. You have the red part is where you have the malicious point. The blue part is where you have the blue point. The arrows indicates the direction of the gradient. And basically, let's say that we already want to perform an adversarial attack that adds only features, because we know that removing might be too complicated because we might just already kill some function. So in this whole area, we can already identify a region where only points where features are added belong to. And this is what we call the feasibility, feature space feasibility region. Now, all the constraints that we just mentioned, about preservable semantic, plausibility, pre-processing, robustness, etc., they do identify, they actually narrow this region even further. But of course, there might be holes and discontinuity. So you can identify pockets of problem space objects. So these are problem space feasibility regions. And you start out with a point X that belongs, of course, to a problem space feasibility region. It's a real object, it's malware. And of course, you know, its abstraction, its projection belongs to the feature space feasibility region because it has less constraint. Now you perform your attack, FGSM, Kalinin Wagner, whatever you want. And basically, ideally, you identify that optimal or kind of close to be an optimal perturbation, delta star, that actually takes your point to the blue region. Now, this, however, might not be realistic, might not be satisfy problem space requirement. In fact, the point might actually lay out from this problem space feasibility region. So you might still be in the feasibility, in the feature space feasibility region, of course, you're out. So what you need to do, once you apply all those constraints that we have discussed earlier, those constraints basically, they are similar to requiring a projection of this point onto one of these problem space feasibility regions. And this projection doesn't leave the X plus delta star as is. It adds an external, another term, eta, which is basically what we call side effect features. So these features are there not for the attack to be successful, that is delta star, but for the attack to be realistic. Okay, and that's all it. it's all about it. So, but these have implications, of course, because how many are these features? Do you need to weigh something that, something that the feature space is completely sparse now doesn't become sparse? Like you can do a lot of reasoning about it. So side effect features that we need to take care of later on. So let me just skip because I guess I am really running too long. So, but this is the way that basically we reformulate adversarial machine learning attacks in the context problem space. So left-hand side, you have the original formulation. You can write it in slightly different ways, but it's that one. And the right-hand side, you do see that our reformulation that takes care of all these constraints, and how this constraint actually makes sense in all that. Paper has tons of details on this. So let me just go very quickly. Maybe I guess I'm really out of time already. Yes. So let me just go very quickly to. I just want to show you the one thing about the feature space. Sorry, the requirement space constraint. I'm sorry, there's already animation and this is Fergus Penalbury, a student that is graduating in a month or so, and I hope that we'll still be able to leverage his graphical ability. So basically, to give you a little bit more context, the way that we perform the problem set transformation, so we do the feature space attack, we identify the features that we need, and then we look at the corpus of benign software and we extract a slice, okay? Not just the features, because that feature might not be plausible. So we do backward and forward slicing to extract just a slice of a blob of code that makes sense, it's realistic, and we implant it relying on software transplantation onto the Android application, and we guard it into this opaque predicate. It's almost done, sorry. So this is also interesting, and then I'm done. So I'll show you the numbers and then I'll sit back there. So the underlying model, because I wanted to set the scene. So the underlying model that we targeted was a linear SVM. Okay. Reason is because this is already very complicated, and we wanted to control as many things we could control, we could understand. So it's a linear SVM. The static analysis is a lightweight static analysis that extracts very simple features in the binary feature space. Very simple to understand. So here, what happens is that you pick you can rank features, and then you pick the features with the highest benign contribution, and then you add it to the malicious software. And this basically has the effect of moving the software all the way around. Then you wrap it up into this opaque predicate, and then you transplant it into the malicious software. Now things are a little bit more complicated. See, it's like imagine that as you do this, the points moves across the decision boundary. Now these are a little bit more complicated because we have side effect features. So you need to actually look at the contribution of the overall gadget of code, and it's easy because it's a linear SVM, so we know these things. Okay. Now once we have that, you run them according to the overall contribution, which includes the side effect features, and then you do the same job. And I'm done on this. Data set is 170,000 Android application, 10% malware. The settings I already mentioned to you. What I wanted to show you is that the bottom line, the line that actually grows the least quickly, is about a secure SVM. So it's an SVM that's been hardened to split the weight to make sure that you use more features, and it's more secure against adversarial attacks. But because we don't have any bound, you see that after 120 features, we're still able to perform the attack in a realistic setting. Now you might argue that 120 features is a lot, but this is out of more than 10,000 features. And even if the feature space is sparse, nothing changes. If you look at the statistics of the application, in terms of size, psychometric complexity, number of permissions, API, it's still everything within the statistics of benign and malicious software. So we don't give away anything too much. Sorry.